Hi everyone. I wanted to apologize that I can't make it. I know you all understand. I also wanted to say thank you for your sweet emails. It really means a lot to hear from you and all of your condolences. So I appreciate that. Thank you so much. So take care of yourselves and then reach out to me via email if you have any questions. I will be available and be checking those throughout the week until next week, and we'll just see how it goes next week. I'll check in with you Sunday evening to let you all know what's happening. So as far as confidence intervals, there are a couple of things that I wanted to talk about to finish up this chapter. Of course, you have multiple videos to watch and resources, but there's just some things that I thought I would show you that I didn't cover, and then also we will go through some MyOpenMath problems together, some examples there. The first thing I want to show you is the effect of changing the sample size. I wanted to talk about that. So if you all remember that a confidence interval is composed of a point estimate plus or minus the error bound for a population mean, or it might be a population proportion. And so if you think about this is what's going to make the confidence interval bigger, or it might shrink it. And remember, our point estimate is x bar. We're going to see later that it could also be p hat for a point estimate, a sample proportion. So if z gets bigger, do you all agree that that will increase our margin of error? And if you think about what would make z get bigger, that would be if I increase my confidence level. So if you can picture the 95% confidence interval, and remember, these z's are like z-scores. It's how far away from the center mean of 0 we are. So if you go above and beyond 2 standard deviations, 1, 2, that is that 95%. And we said that this alpha, z sub alpha over 2, is about 2 and negative 2. We prefer, it's more accurate to say 1.96. So if I increase my confidence interval and I go out to 99% for a confidence level, we talked about this a little bit, but that's going to make my z bigger, my value, because it's bigger than 2, right? And so I'm multiplying by a bigger number. So if I increase my confidence level, that increases the error bound, making your confidence interval wider. Okay? The other way I think about this is if I increase my confidence level to 99%, think about that 99 out of 100 times, I have to be really accurate that I will not miss the true population parameter. Remember, we're trying to capture the population parameter. So I want to be pretty accurate, and I'm going to have to increase my net a little bit and make it a little wider. So that's another way to think about it. So the other way to affect the change is the sample size. And if you think about this, if I increase my sample size, it's just kind of common sense. Our sampling distribution, the standard error for it, gets smaller. So you're dividing by a really big number, this part is going to be smaller, and so that's going to decrease your confidence interval. And think about that with common sense. If you increase your sample size, you are going to get a better representation of your population, right? By increasing your sample size, if it's random and if it's a representative sample. So increasing your sample size causes the error bound to decrease. That makes your confidence interval narrower. If you decrease your sample size, you're going to increase your error bound and make your confidence interval wider. Okay, the next topic I want to talk about is working backwards to find the error bound or a sample mean. So you're given a confidence interval. We'll look at an example in the MyOpenMath practices on this. But you're given a confidence interval. How do you calculate the mean, and how do you calculate the error bound or the margin of error? So it's really straightforward, because with the error bound, you take the difference from the smallest to the biggest interval. Basically, you're trying to find the width of it, how wide it is, and then you divide that by 2 because you know you're adding a little to that sample mean and subtracting a little to that sample mean. So you have two error bounds when you think about the entire confidence interval. And with that, you have to divide by 2. So that's how you find the margin of error or the error bound for a population mean. And to find the sample mean, well, you can think of this a couple of ways. I could take this 0.82 and I could add it to my lower bound, and that would put me in the middle. Or I could subtract it from my upper bound, so working backwards. Or you could just take the average of the smaller bound by taking, the average of the two values, or find the midpoint, kind of like when we had those group frequency tables. So we take the smaller one plus the bigger one, the average of the two, and find the center. Okay, so you could do both of those to double check and make sure you've got it. So that's how to calculate and working backwards. Okay, and for those of you who love algebra out there, I wanted to show you working with this, calculating the sample size. It actually does come from the error bound for a population mean, and by squaring both sides and solving for n, this becomes the lovely formula for that, where z is that whatever confidence level you're at. We're going to use Larry Green's calculator for that, and I'm going to show you some examples from the MyOpenMath, but I just thought you'd appreciate that. And I know you're watching all your videos, so I don't need to tell you, but be sure to watch this one. It's really fun on small sample inference for one mean. This is all about t-distributions. It's a very interesting a video with Party. You know how we like to party with Party. And it's really helpful in understanding what a t-distribution is. And it introduces the concept of the degrees of freedom and a little history behind it with the brewery. Pretty Things Brewery. So the history, a little bit about the history, is statisticians, they were using normal distributions. They found that with these normal distributions, when they didn't know the big population standard deviation sigma, and they were using the sample standard deviation S, it wasn't quite good enough. It wasn't capturing and creating good enough confidence intervals. So it was William S. Gossett, who worked for the Guinness Brewery. He came up with this different distribution. It's known as the student's t-distribution. Very close to the normal distribution, but there are a couple of different things. So you can read that history. I'll let you pause it if you want to. But we used to calculate normal distributions sometimes and then do the t's. Now, if we don't know sigma, so if sigma is unknown, use S, and remember, that's from a sample, and that's your standard deviation. You can find a standard deviation from a sample using Excel. Just like we did averages the other day, you highlight it all, you do your equals formula, and then highlight the cells and select sample standard deviation. I think it's STDEV from a sample. So that works in Excel or Sheets. Okay? So we're going to be using this standard deviation, the sample. It's more realistic to only have the standard deviation from a sample, but if we do that, we have to use the t-distribution. So the important thing with t-distributions, you have to know the degrees of freedom. And it's actually easier than you think. It's kind of challenging concept or name, right? But I like to think the degrees of freedom. So all you do is you take one away from the sample size, and that's your degrees of freedom. Okay? So here's what the t-distributions look like. I'm going to show you in Desmos in a second. This is the t-score. It's kind of like our z-scores that we had before when we introduced sampling distributions. They looked like this. You have sigma divided by the square root of n. So see the only difference with our z's versus t's. We've got x and mu, same thing, but notice that it's sample standard deviation versus sigma. T-scores are the same. Your t-distribution is centered around 0. And the number of standard deviations You go out 1 standard deviation above or below 2 standard deviations, just like z-scores. The only thing that changes with the t-distribution is what your sample size is, because sample size has an effect on the distribution. And it makes sense that if you increase your sample size, your t-distribution, I think it's right here, approaches, let's see, where is that? T-distribution has more probability in its tails, so the graphs of the student's t-distribution will be thicker in the tails and shorter in the normal. We have the mean of the t-distribution is 0. The graph is similar to the standard normal curve. The exact shape of the t-distribution depends on the degrees of freedom, and here it is. The degrees of freedom increases, the graph student's t-distribution becomes more like the graph in the standard normal distribution. I'm going to show you how to graph these in Desmos in a second. The other thing, we have to sort of assume that the random sampling assumed is completely separate from the assumption of normality, and that the underlying population is normal. Okay, so I'm going to type in normal distribution just to show you the difference, 0, 1. That's the standard normal distribution, and we'll just take a look at that, and we'll compare it to a t-distribution. And notice that it says, it prompts you to say the degrees of freedom. So I'm going to show you what happens as the degrees of freedom change. So let's just say we have a degrees of freedom of 10. And I'm going to zoom fit this, like that. Let's zoom out a little bit. I just kind of want to, maybe we should do a smaller degrees of freedom. Well, that's good enough. You can kind of see. Notice that I mentioned the degrees of freedom is, this would imply actually not that our sample size is 10. It would imply that our sample size is, that's right. Did you say 11? I know you did. I know you all did. So the sample size is 11. Notice that there's a bit of area in the, and I'm going to see, this is sometimes doesn't work so pretty, but I can sometimes write on this. But notice that there's some area right here, a little bit of extra probability in the tails of a t-distribution. Okay? So we're going to increase our degrees of freedom now. So let's just do that. If I increase my degrees of freedom, notice what happens. 20. I guess I saw that dramatic, so notice if you only have a sample size of 3, degrees of freedom is 2. Remember, it's 1 less. Sample size of 6, so that would make the degrees of freedom 5. Notice the area in the tails, the extra. Remember, it's always, probability has to do with the area under the curve. And so there's more area under those curves on the tails. And that's just because of that fact that we're using a sample standard deviation now. We are no longer using the standard deviation from the big population, which is more like, if we could know that, it would be better, but that's not realistic, right? So that's what's happening with the t-distribution. If I put this, if I did my degrees of freedom to 99, say the sample size was 100, you can't even tell the difference, right? So as long as our sample size is large enough, we have a very accurate graph, and we can find very easily great confidence intervals and probabilities with this because of our sample size being so large. Remember, we're dealing with inferential statistics. So we're making an inference about the big population from these samples. So this is a big deal if we can do this. Okay, remember you have this chart in this week's module, and I gave you a copy of it, so you have an actual hard copy of it, but I just wanted to point out these great things. Oops, I thought that was a highlighter. So confidence intervals, if sigma is known, that's what we were doing in our first session this week, and we talked about the structure of it. It was this critical Z value. If you recall, this is how you put it into Desmos, exactly like this with your confidence level. So if your confidence level is, for instance, I say I want to find that critical value for a confidence level of 90%. So I could actually copy and paste this if you downloaded it as a Word document from Canvas. And I do my 0,1 right here. I'm just doing this from above. And I could put that 0.90, and then alpha, remember, is all the other stuff other than the 90%. And that's the probability of missing and when I'm trying to capture my true population mean. So that's that 0.10 divided by 2. I could actually put this into Desmos just like that. If you recall, 0.95 is that, and that's not for the middle 95%, that's for the middle 90%. So that's when we're calculating a confidence interval for a 90% confidence interval. So inverse CDF, then we do our normal dist, you can see it right below, normal dist, and this is all into Desmos, like that. That'll give you that critical Z value. Remember, that's a Z-score. It's just telling you the Z-score. So you plug that in there, you plug in whatever the known standard deviation is, and you plug in your sample size. That'll give you your error bound for a population mean. Okay. So now I'd like to go into the, and we'll get a different color for this, it's kind of fun. We'll go into confidence intervals if sigma is not known. Notice that these are t-distributions, okay? So we're going to use the sample standard deviation, or S instead. S is the sample standard deviation. T-distributions. Now, in this case, this is the structure of it. To find that, we actually have to go into Desmos, and I'll do that for you. You have to know the sample size in order to do that. So your critical T values, those T sub alpha over 2, is going to depend on what your degrees of freedom are. We used to have these long charts, different columns for confidence intervals, and then the degrees of freedom depending on your sample size, and then you'd go in and see what those critical T values are. But we can do this in Desmos, which is pretty nice, and honestly you don't need that for the myopia math because we can use Larry Green's calculator, but I will show you this one time so then you have it. So notice that it's this highlighted down here, the inverse CDF, T-dist. So remember, Desmos tells you to undo a function with inverse CDF. I'm undoing this t-distribution, but the t-distribution needs to know the sample size, which is not the sample size, but the degrees of freedom, which is 1 less than the sample size. And then it's the same idea. So if I'm doing a 90% confidence interval, I'm going to do that 0.90 plus half of my alpha, which is 0.95. So let me show you how to find that. So we're going to undo our function, inverse CDF it. And what am I undoing? What function? I'm going to undo the t-distribution. Suppose my sample, I'm just going to throw out a sample. Suppose our sample is 30. So our sample was 30. So then our degrees of freedom would be 29, comma. You're going to put in that 0.90 confidence level plus alpha over 2. And I can do this all just like I did in that chart. So then it'd be parentheses 0.10 divided by 2. And I'm just doing, that's half of alpha. Does everybody see that? So that gives me that value. And I'll just show you in the graph what this means. Okay? So I'm going to graph that t-distribution with the degrees of freedom of 29. And I'll find that cumulative probability. Remember, we were trying to find that 90% confidence interval. So if I put this value in, the 1.699, negative 1.699, and I go up to 1.699, notice that what is the middle, the proportion that you see in red, is that 90% if you round up, 0.90. Do you see what we just found? So that is our critical t-score that we need to use to calculate our margin of error. And let's just finish it out. If I said, I'll try to write with this. If I said that my sample was 30, oh, see, this is what happens. It always happens. Sample was 30. It gets a little messy. And my standard deviation, I don't know, I'm just making it up, is 3 then to calculate the margin of error, it would just be that critical t-value of 1.69. Just, it's slow. And then times your standard deviation. It just goes really slow. I gotta write slowly divided by 30. So I don't put the degrees of freedom in there. I still use the n value for that. So does everybody, and I'm going to put a little dot there. No, just a dot, not erasing it. That's 1.69. You guys see it, 999. Do you get the point? So this is the margin of error right here that I'm looking at, okay? We'll go back to Word so I can write. Okay, so now I'd like to show you some of the examples from the MyOpenMath this week. You have a few practices to do. So this LibreText, there's a link to new LibreText stats calculator that I'd like you to click on. But just while we're here, keep in mind we have our lecture PowerPoints, and these are all the different videos that you can watch for this class, for this chapter. These are short videos, like I said, in class, and they just explain and work through the LibreText calculator. So here's the link to the new LibreText, so go there. And then we're going to go down and look for, let's read the question first. I know it's going to be a mean. I'm on chapter 8, confidence intervals with a mean. So if I go into that and I look at question 2, and I hope you can read this okay. I can zoom in a little bit more. So you are interested in finding a 90% confidence interval for the average number of days of classes that college students miss each year. The data below show the number of missed days for 13 randomly selected college students. So 13 is my sample size. Round answers to 3 decimal places where possible. So what I'm going to do is I've got a mean. When you deal with proportions, it's like, think of a binomial distribution. It's either a success or a failure. You're either part of the club or you're not. So a proportion is part out of the whole population. So we're going to do confidence interval for a mean with data. So we have data, and I just want to show you how slick this is. You should be able to highlight this, Control C, Control V, and the other beautiful thing about this is I don't even have to worry about my spaces. You can have multiple spaces. As long as you put a comma in between each of these, you will be okay. So confidence level is 90%, but I have to put that in decimal form, and then I hit calculate, as Larry Green would say. So this right here, do we know, in this case, we are not given sigma. So it doesn't even ask you what sigma is. In this case, we are dealing with a T distribution. If you do know sigma, that's a Z distribution, okay? And then I'm just going to make sure we have our values that are accurate, because sometimes there's like a slight thousandth of a point off, but we look good here, 0.824, yeah. See, there's an example. See how it's 8.295, and here it's 8.294. So I think that's just calculating error with different calculators. So if you keep getting something wrong and you're certain that you got it right, or if only part of it's wrong, you might need to round up. And you can also notify me if you don't want to do it again. I'll just give you another point or whatever you missed for that. So that's just something to keep in mind. In this last part, if many groups of 13 randomly selected non-residential college students are surveyed, then the different confidence interval would be produced from each group. We know that about 90% of these confidence intervals will contain, remember, 90% are going to capture the true population parameter. That's big, mean, mu, right? And about 10% of them will miss. Okay, so I'm just going to put that there because my writing when I'm not in Word doesn't work as well. So that's an example for this. I'm going to show you 2 other ways to represent this though. So the other part is, notice that in question 3, they're asking for a confidence interval, but it's in this format where mu is in between. And I'll talk about that in a second. And then also This one, they want it to be in an open interval. See the red in there? So the, excuse me, the open interval like this. So you're going to do parentheses like so. That's how they want to see it. And then this would just be the lower bound would be on the left, the upper bound would be on the right. So that's how it would work for that. And just to point that out, I put this in our chart. The confidence interval can be written as an open interval. So this is your lower bound and your upper bound. And it's also as an inequality. Notice mean is in the middle. This is your lower bound, lower, and this is your upper bound. Okay, hope that makes sense. I think we're going to move on to proportions now. So I was looking over the PowerPoint. There's a lot of extra algebraic formulas in there that I don't really think you need to worry about. So I actually like how I wrote it up in this column, and maybe we can zoom in so you can kind of see it a little better. Okay, so I'm going to focus on the confidence intervals for proportions here. And if we do that, remember that p hat, the first thing that we need to talk about is p hat. And p hat is from a sample proportion. So if it's wearing a hat, it's from a sample, not a population. So no hat, then it's the population parameter, which is the population proportion. Okay, so p hat, if you think about it, I think I asked you all, what was it that I asked you in class today? There was a question. Oh, how many of you were Tuolumne County residents? And a few of you raised your hands. I was surprised at how many didn't. There's a lot of Calaveras residents, right? So X would be the number of folks that lived in Tuolumne County out of the total sample size, out of the total class. This is the structure of the confidence interval. You really won't need to do this much and use this too much if you use Larry Green's calculator, which I'm actually okay with. You calculate your z's just like you did before for the inverse CDF, undoing a normal distribution 0, 1, and you put in your whatever the area to the left of this critical z value is. These are equivalent because Q hat is the number of failures. I don't know if you remember that from our binomial distribution time, but you can also think of this as 1 minus p hat. So it's the product of the probabilities, the success and the failure idea, divided by n and the square root. That's how you find the standard error from a population proportion. Okay? The point estimate, once again, a confidence interval always has the same format. It's a point estimate plus or minus margin of error. And to be more specific with proportions, it's the error bound for population proportion. Okay, and confidence level, we can use the same thing like I said. So we're going to jump into examples, and we're also going to talk about sample sizes from the MyOpenMath practices. Okay, I just wanted to show you a couple of the sample size questions. So this is from the Chapter 8 MyOpenMath practice with sample size title. A political candidate has asked you to conduct a poll to determine what percentage, so we're dealing with proportions, percentage of people support him. If the candidate only wants a 2% margin of error at a 99% confidence level, what size of sample is needed? When finding the z-value, round it to 4 decimal places. We actually don't even need to because we're going to use Larry Green's calculator, and you can do that for all of these. So a sample size for a proportion is what we want. So we're going to click on the sample size for a proportion, and we're going to zoom. Notice that there is no, I need to make this bigger, don't I? There is no, like in this case, estimate for what P is. Do you all see that? They're not saying, this candidate has no idea how many people are supporting him. So all we can work on, and I don't select have the estimate, all I can work on is this idea that the error, I don't want it to be more than 2%. So I go 0.02 and my confidence level is 0.99. So everything has to be in terms of that decimal form. And then I'm going to calculate in, and sorry, it's off the thing, but you can see that it's 41.5. 4,147 people for my sample in order to be this accurate within 2 percentage points. So with an unknown proportion of how many people favor this candidate. Okay, so we're still on the sample size practice. I wanted to do question 5. This time we actually know, in this case, based on previous evidence, you believe that the population proportion is about 24%. And we want to obtain a sample, and we need to know what our sample size should be. We want a 90% confident, like to be 90% confident with our estimate, and that our estimate will be within 2 percentages of the true population. So once again, if you look over here, you're going to do sample size for a proportion. You can see all these percentages. We're dealing with a proportion. We do have an estimate for P. That estimate for P is 0.24. The error is 0.02 again. And the confidence level is 0.90. So these are all pretty straightforward in this practice. And that is your sample size. So you need to have a minimum of 1,234 people in your sample to guarantee that your estimate is going to be within 2 percentage points of the true population proportion. Remember, we're trying to capture the true population proportion with a confidence interval. So that would be like my margin of error, above and below. Error bound for a population proportion. Let's do one more. I think I can just scroll down. And in this one, notice that they give me sigma. Sigma. That has nothing to do with the population proportion, does it? Okay, so I need to go back to Larry Green. So I hit the back button on my browser and I go down and I want to see, estimate the population mean. We want to obtain a sample to estimate the mean. Based on the previous evidence, we believe that the population standard deviation is approximately 29.2, so that's sigma. And we want to have a 98% confidence level, and we want to be within 4 units. Whatever your units are is the error. So you don't have to put that into decimal form because we're dealing with means in this case. So maybe I want to be within $4 of the true population parameter of what students spend on their meals per week, something like that. So I'm going to see the sample size for a mean, and I have to put in sigma 29.2. I know my error is within 4 units, whatever the units are, like I said, and then it's 0.98, and I hit calculate. So the minimum size that I should have in my sample is 289. So that's sample size. And that should go really quickly. So you got 1 checked off. All right, everybody, this is the last example, I promise. So I wanted to show you a proportion. This is from your practice with proportions. It's Confidence Intervals, Chapter 8 with proportions. And remember, you have your chart with 3 columns listed out. I know it's a proportion because I'm dealing with the adults, and of which 215 had kids. So to give it some context, we're dealing with the percent of adult residents in a county, and what percent of them are parents. So we sampled 500 adults. We found out that 215 of those 500 had kids. So first of all, if I ask you just, what is that proportion? Well, P hat is going to be let me just do that. Kind of like these sparkly ones. They're sort of fun. So if you needed to know P hat, that's the sample proportion, would be the 215 out of 500. So that's just for your information. And that's our point estimate. That's our sample proportion. If we do a 95% confidence interval, I'm going to use that same exact value, my critical Z value, Z sub alpha over 2. And that's going to be that 1.96. And then if I wanted to find my margin of error, I have to calculate and find the standard error. And this is that kind of bigger formula that I was telling you about. So it's the probability of success, which is 215 out of the 500, times the probability of all the other folks. So that would be the 385, wait, what would that be? 200, nah, can't add, it's late. 285 of the individuals out of the 500, and then it's divided by the sample size, which is 500. That's your standard error or your standard deviation for this. So it makes you appreciate this to find your actual proportion. If I put this in Desmos, I'll open up Desmos so we can see it. So just to save time, and I figured you could pause the video if you want to see this, and I would encourage you to type this into your computer, into Desmos as well. But this is the old-fashioned way back in the day when we had to walk 10 miles to and from school in the snow. This is how we would calculate a confidence interval. We know that critical z-value, c sub alpha over 2, this is for a 95% confidence interval, right? This is the standard error, this part, just as I had labeled. And often I don't even calculate what the actual proportion is. I mean, you could just by plugging in to see what the proportion is. It'd be 215 divided by 500. Okay, so it's 43% of the this county's residents have kids, right? So that does give it a little context. And then that's our sample, our point estimate from our sample mean. So I'm putting on that 0.43 minus some margin of error, and I'm taking that 0.43 and I'm adding some margin of error to it, okay? So the other part that I want to show you all is, if you didn't know that, what your margin of error is, first, actually, we need to go back, right? Because I want to show you, and if you didn't know where to go, we're dealing with a proportion, and we want to find the confidence interval. There aren't many choices here. So confidence interval for a proportion, I'm going to put in my sample size of 500 adults that were sampled, of which 215 had kids. That is a little under 50%. My confidence level is 0.95, and I'm going to hit calculate. So I've got the same values as we did in Desmos. So you can keep that in mind. Look at that. It even gives you your sample proportion. Remember, we could calculate that on our own. 215 divided by 500 would give you that. So when you put this in, and I'm just for time, oh, wait, I forgot. I did a screenshot of this so I could actually write in it because I'm in Word now. So I can draw. Let's do some other fun colors. What colors? Let's do sparkles. Okay, so we're going to do sparkles, and I could write my proportion as 0.3866, and I think we need to go to, did they say 3 decimals? Whoops, don't do that. You got to change that to a 7, and then the other one is 0.473 for my answer. That one's hard to see, isn't it? All right, we'll go back to plain old black. All right, so this is my answer for the estimating. Remember, P is the population, true population parameter, proportion, okay? Now, just as a quick refresher, suppose you only had the lower bound and the upper bound. You wanted to find that point estimate. Well, that is the 0.43. Okay, that was given here, but you could also do that by finding the average. So we're going to take those two values, and I'll show you in Desmos, just as a refresher, how to find them. So we're going to go, and if I do, remember, if you take the difference from the lower bound and the upper bound, so 0.473 minus 0.387, and then I put parentheses, I better put parentheses around them all. And then I hit / and 2, that'll give me the margin of error, 0.043, okay? So that is going to go right here. And you can always check your work to figure out what this point estimate or the sample proportion is if you didn't know, if all you knew was the confidence interval, 0.473 plus 0.387, and do parentheses around that So I can divide the whole thing by 2, oops, /2, and notice that's where your sample proportion comes from. So that's just working backwards from a confidence interval. Okay, everybody, I think that was it. I hope it wasn't too long, but you can pause, take breaks as you need to. But I think that should get you through confidence intervals. So watch it, tell your friends that it was helpful, have them watch it, have a wonderful weekend, and thanks again for your sweet emails. I really do appreciate you all. You've been helping me through this semester just with great distractions, and I admire you all. So it's been really fun working with you, and I miss you already. Okay, talk with you soon. Bye.